So we have to talk about the review. So questions from you guys, Tala? So you could make this not so hard or a giant pain in the butt, depending on how you approach this. I'm going to do it as the not so hard way versus the giant pain in the butt, because I'm not about making my life harder. You know what I mean, guys? Life's hard enough, right?
Yeah.
So I would start by factoring everything. So if you didn't factor things correctly, that's going to make life problematic. Although hopefully that most of us are pretty good at factoring these kind of things and can do it pretty quickly. Right away I noticed that inside the parentheses I can do a little bit of reducing. And now I have two options at this point. I can either work inside the parentheses first, or I can distribute into the parentheses first. So looking at the options here, I notice that if I distribute first, the x plus 3's would cancel, and the x plus 2's would cancel. And similarly, the x minus 4's would cancel, and the x minus 3's would cancel. And gee golly willikers, that seems like a much better idea to distribute first. So when I do that, the stuff in yellow will cancel out, and I'll be left with just the piece in green when I distribute in. And when I distribute here, the stuff in green will cancel, and I'll be left with just the stuff in yellow. So now I'm left with just making a common denominator and dealing with this piece. And hopefully, looking at this, it should be pretty obvious what that common denominator would be. So when I multiply things together, I get this. And when I combine the like terms, I get negative 2x plus 1 over x plus 2, x minus 3. Oops, but I also have to deal with the restrictions, right? So I had this piece, I canceled all the x plus 1's, I canceled out all the x minus 2's, I canceled out all the x minus 3's, I canceled out all the x, oops, not these ones, sorry. I canceled out all the x plus 3's, and I canceled out all the x minus 4's. So that stuff as well. I didn't cancel out these ones because, see, they're still left at the next step. Okay with that, Itala?
Yeah.
So again, like, two ways you could approach that, and if, as long as you like chose that order, things were relatively manageable. If you tried to like, oh, I'm going to just start by making a common denominator and multiplying these things together without even factoring, you made a bloody mess of it. So again, like, take a moment and look at, do some factoring, and then look to see what the easiest route's going to be. Okay, next, Claire. So how did you try to do 8, Claire? Okay, well, okay. Well, there's two ways you could do this. You could either clear fractions or make a common denominator. Those would be the two recommended routes. Let's make a common denominator for the sake of argument. So if I look at all the denominators, hopefully it's pretty clear that the least common denominator would be x times x plus 3. So what do I have to multiply this fraction by to get the common denominator? X plus 3. What do I have to multiply this fraction by to get the common denominator? X times x plus 3. And what do I have to multiply this one by? X. Everybody happy with that? Now that I have a common denominator on both sides, I can just ignore the denominators and just worry about solving the numerator. So we'll just distribute these things through. Oops. Minus. And this is a quadratic equation, so let's move everything on the same side. And to solve this, I could either try to factor it or use the quadratic formula. I don't think that this thing factors, and the leading coefficient isn't 1 anyway, so factoring it's not going to be quick, so let's just use the quadratic formula. So we have that. This is 9 plus 120, so 129. And that doesn't simplify, so this would be my final answer. And quick check, obviously, like if I plug that in, it doesn't give me a zero denominator anywhere. So since it's irrational, almost squared away, you'd not know that there's no big problem there. Atala? I mean, you could do it that way also. That's clearing fractions. So if you have so now if I multiply by x times x plus 3, the denominators all go away and I have this, right? So it's a question of when do you want to clear the fractions. Judging from the set of tests that I looked at last time, a minority of students felt good about clearing fractions. Most of you tried to make common denominators. So I just accepted that and chose to do this way, even though it's the exact same thing. You're just making an extra step out of it. But whatever. Okay with that, Atala? Okay. So it's the same thing, it's just writing an extra step. But it seemed like everybody wanted to write that extra step on the quiz. So I've just accepted that as what you're going to do. So I showed you how to do it with the extra step in there. Because I saw lots of people get to a common denominator like, okay, now just take the numerator and solve it. And everybody kept on going and doing weird things and like trying to cross multiply and making a big mess. It's like, oh dear. So, Justina. So I would take this answer, and I'd look at the original problem and plug that answer into the denominators and check to see if it gives me a zero denominator. Any denominator being 0 means it's extraneous. Doesn't matter where it is or how many times it happens. If there's one 0 denominator, that solution is extraneous. Okay? Sierra, you had your hand up. The key features are listed on for number 11 and 12. So it's literally those 4 things that are on the sheet on the previous part. Nathan?
Yeah, so number 9 and 10, I understood everything. I didn't understand number 9. Maybe that would be a lot.
It's just y equals k. So simple rational functions are in this form. So the horizontal asymptote is that. The vertical asymptote is that. Well, that's different. That's different. You asked about 9, though. So 9, it's just simply k, right? It's the horizontal asymptote. 10, it's different. So 10, if you have like y equals ax plus b over cx plus d, the HA is the leading coefficient over the leading coefficient, and the vertical asymptote is the denominator set equal to 0 and solve. So this would have been like 9 and then 10. But that's how you found those things. Remember, this is the same thing. This is degree of the numerator equals degree of the denominator, right? So how do you find its end behavior? Leading coefficient over leading coefficient. Still the same rule that we had for the general works here, right? Because the general is more, covers more cases, but it requires that it's written as one fraction, so you can't use your rules for the general for this one because it's written as 2 fractions because of the plus sign there. But your rules for the general that you know will work for this case also if you forgot those little shortcuts. You could treat it like a general rational function and still be able to get all the same things because it's still 1 fraction, right? Is that okay, Nathan? Yes, sir? So I'm going to start by factoring this because to find the domain, I got to set the denominator equal to 0 and solve. That's that. So if I set this equal to 0, I get 2. If I set this equal to 0 and solve, I can't factor it, so I'd have to use the quadratic formula. But that gives me imaginary solution, so it doesn't matter. With 1? With the trinomial part of a sum or difference of cubes. No. No. You could certainly have, like, you stop talking, please. No. Just because it's a trinomial that you have to use the quadratic formula doesn't mean you're going to get an imaginary solution out of it. If this was just minus 4 instead of plus 4 for whatever reason, that would be solvable, and you would get irrational things, but they are real solutions, and you'd have to list them with your domain. Stop talking, please. So you literally have to actually check it with the quadratic formula. And if all it is you typing into the program on your calculator, that's fine. But like, you actually have to check it. Yes, I'm not. Yes, thank you.
So we wouldn't include dot x squared plus 2x plus 4, right? Like in the domain.
No, I did, but there's nothing to include from it because it gives me imaginary solutions.
Yeah.
Okay. So now I'll reduce. And I go reduce down to this, right? So because I did reducing, I get a removable discontinuity at x equals 2. And I can find the y-coordinate for this now by, where do I have to plug the 2 into? I plug it into this. So that gives me 4 over 12, or 1/3. And And there are no vertical asymptotes because this part has only imaginary solutions to it, right? Because it has only imaginary solutions. Same reason why I didn't contribute to the domain at all. So the x-intercepts, I look only at the reduced version. That's negative 2, 0. And the end behavior, I look at the reduced version. Degree of the numerator is 1, degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, I have either x or y equals 0 or y approaches 0. Since I do have an x-intercept, I know the line y equals 0 is crossed, so it should be the y approaches. And that was the 4 key features there for that one. $16. Okay, so I'm going to just start by trying to factor this. So my domain, this piece gives me x not equal 0. This piece gives me x not equal 3. This piece gives me imaginary solution, so it doesn't contribute anything to it. Sierra, you have a get out of jail free card. Here I notice that this piece cancels out. So I have a removable discontinuity at x equals 3. And when I plug that in, I get negative 6 over, let's see, 9, 27 times 3 is something real small. Let's see, that was negative 0.0741. And now this piece gives me the vertical asymptote, because that still can be 0. Does this piece do anything for the vertical asymptote? No, because it gave me imaginary solutions. So I have those two things. My x-intercepts are going to come from the non-reduced, or the reduced portion, excuse me. So that's just 9, 0. And then my end behavior, well, I notice the degree of the numerator is less than the degree of the denominator. So it's either y approaches 0 or y equals 0. And since I have an x-intercept, I know the line y equals 0 is crossed, so it's just the y approaches. So now we'll make our table, vertical at 3 points, vertical asymptote. 3 points, vertical asymptote, 3 points. So let's see, let's put the 9 out here for the x-intercept. So that's 6 away, so I'll put negative 6 out here. And then I guess I'll put, how did I do that? I'm stupid. Guys, who's not yelling at me? Shame on you. Thank you. I only have one vertical asymptote, you big fat dummy. So I'll do negative 9 over there. I guess I'll slap in the removable discontinuity. And then, I don't know, I'll just pick something like 1. So to match those other pieces up, I'll do -1, -3, and -9 over there. Everybody's all right there? Okay. I'll go to my calculator and get the y values out of this. So there's that. And then, I don't know, let's go up by 0.2s maybe. 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4. And go down by the same, so -0.2, 0.4, 0.6, 0.8, -1. So I have my vertical asymptote here at x equals 0. I have my horizontal end behavior here at y approaches 0. And then let's plot some stuff. So I have 1 and 1.4, 3 and 0.44. Oops, that's not 3, that's 3. And then 9 and negative that. So it looks like that piece over here. And I have -6.2, and then almost 0, and actually 0. So let's say we do something like that. Okie dokie. All right. Who's next then? Just tell me what you want me to do.
Oh, what time do we get out? Two more times. Oh my gosh. Isn't that right?
So I'd start by factoring the denominator. And then let's try to do this the same way we did the previous one by making a least common denominator. So notice the least common denominator will be. So what do I need to multiply this fraction by? Are you sure? Nothing, right? What do I need to multiply this fraction by? Okay. And what do I need to multiply this fraction by? Okay. And so we have this, right? And because the denominators are the same, we can forget about them now. And whoop, whoop. Move everything onto one side. So let's say we have 11x over here and 33 over there. And divide both sides by 11, we get 3. Is this really an answer, though? No, because if I go back to the beginning, if I plug it into, say, this one, what do I get? 0 denominator. So we throw this out because it's extraneous. And since we have no solutions left, we'd say no solution. What now, brown cow? You can. Okay, we're all done then? For 13? Yes, you basically just put it into a chart and make the chart graph it. That's all I'm asking you to do. We can try. So I'm going to start by factoring. I'm going to factor the numerator by grouping. I'm not going to show it in the interest of time, but it does factor down to give me that. I think I showed it on the review sheet. So the domain there is all real numbers except for plus or minus 1. We can reduce those out of there, so we have a removable discontinuity at x equals negative 1. And when I plug negative 1 in up here, I have negative 3 times 1 divided by negative 2, so that's just going to give me positive 1.5. And I still have that x equals 1 left in the denominator, so that gives me the vertical asymptote at x equals 1. The numerator pieces give me my x-intercepts of negative 2, 0 and positive 2, 0. And then since the degree of the numerator is greater than the degree of the denominator, I know we're going to have a slant asymptote, right? That's Rachel? Okay. So to find that slant asymptote, I have to do polynomial division. What I'm going to want to use is the reduced version to do that. But doing the reduced version of that, I'm going to need to have to FOIL that back out in order to do the polynomial division. So I have x minus 1 times x squared plus 0x minus 4. Notice I included the 0x just as a placeholder. X times x gives me x squared, and then multiply to the negative 1 to just kind of carry it through. X squared minus x squared is 0. 0 minus negative 1x is positive x. So negative 1 times, positive 1 times x gives me x. Subtract down, that's negative 3. So the quotient there gives me my slant asymptote. Sarah, in the interest of time, can I stop here after I've done all this stuff? Okay. Okay. Rachel? If it didn't make it to the review, it won't make it to the test, unless it's an extra credit question. Okay? All right, my peeps, we done.